Hello guys, welcome to Dre Educational Consult and welcome to our 7 days tutorial, and I'll be taking you chemistry in this 7 days tutorial. So today we'll be talking about organic chemistry. We all know that chemistry is largely divided into some sections. We have some groups like the physical chemistry. We have other group like the organic chemistry. We have the analytic chemistry. So out of all these categories, we are going to be talking about the organic chemistry. Number 2. So we have other groups in chemistry, but we'll be talking about organic chemistry today. So what is organic chemistry? Organic chemistry is the scientific study of the composition, take note of that, of the composition, the structure, their properties, the reactions, and the preparation of carbon-based compounds. So when we are talking about organic chemistry, these are some of the key words that we should be looking at. We are looking at the composition of carbon-based compounds. When we are talking about composition, we are talking about the ingredients of carbon-based compounds. And next, we'll be talking about the structure of carbon-based compound. That is the framework of the molecules that make up organic compounds. And next on our list is the properties. That is, when we talk about properties, we are talking about the characteristics of organic compounds. That is carbon-based compounds. And next, we are looking at the reactions that these carbon-based compounds undergo, the changes, the physical changes that they undergo, the chemical changes that they undergo. And lastly, we'll be looking at the preparation of all carbon-based compounds. So when we are talking about organic chemistry, we are looking at this all related to what? Carbon-based compounds. So this is all we are going to be talking about organic chemistry. This is the entirety of organic chemistry. Any organic chemistry that you'll be taught of is either the composition of molecules, the structures of molecules, the properties of molecules, the reactions of that those molecules undergoes, and how those compounds are prepared. Now, we are looking at the uniqueness of carbon. We said that when we are talking about organic chemistry, we mentioned it here that we are talking about carbon-based compounds. Why is it that organic chemistry is all about, or is so when we are talking about organic chemistry, why do we say carbon-based compounds? Why is carbon the principal element in organic chemistry? We have different elements on the periodic table. So why is carbon chosen? There are some unique properties of carbon that make carbon the principal element in organic chemistry. Some of those characteristics or uniqueness are things like the catenation of carbon. So we are looking at the catenation of carbon. We are looking at the tetravalency of carbon. Of carbon. When we are talking about the catenation of carbon, we are talking about the ability of carbon to be able to form a stable long chain covalent bond with itself. Take note of that. When we are talking about the catenation of carbon, carbon is the type of atom or an element that is able to bond with itself and form a long chain of bonds, a covalent kind of bonds, either in a straight format, in this format, or we have in a branched format, or we have even in a cyclic format. So this atom or this element has the ability to undergo this phenomena that is known as what? As catenation. The ability of carbon to bond with itself to form a long chain. And we also have another unique property of carbon, which is tetravalency of carbon. We all know that carbon fall on the group 4 on the periodic table. It fall on the group 4 of the periodic table. And we all know how an element fall on a group when designing our periodic table from our elemental chemistry. When an element fall on a group, let's say for example group 4, it means that element has 4 valence electron. 4 valence electron. So in the case of carbon, carbon has 4 electrons that are found on its outermost shell or the outermost orbital, and this gives you the ability to form bonds in about 4 places. So this is another unique properties of carbon that makes it to form large group of compounds, large group of organic compounds. We also have some other elements that are on the group 4 on the periodic table. And we may ask the question, so why is silicon on the periodic table and it doesn't have the ability to form carbon-based compound? It doesn't have the ability to stay strong, attach covalently to other atoms, and form large molecule of compounds, just like the carbon. Though silicon fall on the group 4 on the periodic table, but it doesn't have the same bond energy that keeps a carbon atom as rigid as it is. So though silicon may form covalent bonds in 4 places, but the power or the energy of this bond is not as strong as that of a carbon atom. So after that, we are looking at how or where can we find these carbon compounds? Where are the sources of these organic compounds? Where can we see them? We can see them in several places. Places like plants. We can see them from plants origin. We can see them from animals. We can also see them in minerals. So examples of organic compounds that are found in plants, we have the starch. The starch is an example of organic compounds. It belongs to a group of organic compounds which we call the carbohydrate. So it's an example of organic compounds that can be found in plant. We also have another source, which is the animal. We have organic compounds that can also be found in the animal. We know a lot of it from our biology. We have compounds like the amino acid. We have compounds like glycogen and several other compounds that are carbon-based compounds that are found in what? In animals. And lastly, we're going to be looking at another origin of carbon compounds, which is the minerals. We have carbon-based compounds like the petroleum is a very, very common thing. It's an example of a carbon compound. We have others like the methane, which is known as the natural gas. It's also an example of what? Of carbon-based compounds. Now let's look at the next thing on our list here, which is the functional group. Next on our checklist is the functional group. Now in organic chemistry, there are thousands or even millions of organic compounds, and these organic compounds are grouped into families. They are grouped into family, or what we call the homologous series. They are grouped into family or the homologous series. Now, this homologous series, they have different characteristics. They have different chemical characteristics, different physical characteristics, and they are distinguished from other organic compounds. Now, the major thing that distinguishes groups or families of organic compounds are what we call the functional group. Very important. The major thing that determines group of organic compounds from one group of organic compound or family of organic compounds to another family is what we term as functional group. So is that element or is that thing, we can call, if we decide to call it a thing, that say, okay, this group of organic compounds, they belong to this family, or this is their family name, and they are different from this group which have this family, and this is their family name. Now, when we are talking about functional group, we are talking about an atom or group of atoms that give a group of organic compounds their characteristics. Take note of that. They are atoms or group of atoms that give an organic compounds their characteristics or distinguishes that compound from another group of organic compounds. Just like I said earlier, there are different groups of organic compounds. Now, we have different functional groups. We have something like the hydroxyl group, which is represented as this. We have another functional group, which is the carboxylic group, which is represented as this. We have the alkyl group, which is represented as this. Now, this group of atoms are what we refer to as functional groups. Once you see an organic compound that have this group of atoms, which is made up of oxygen and hydrogen, you have an organic compound A that have this group of atom OH. You have another organic compound B that have group of atoms COOH, and you have another organic compound C that have group of atoms OH. Now, this group of atoms, since they possess the same group of these organic compounds, organic compound A and organic compound C, since they have the same group of atoms, the hydroxyl group, then they share the same characteristics, and hence we say they belong to the same family, or we say they belong to the same homologous series. Now, we have several other examples of functional group in organic chemistry. As time goes on in our tutorial, I'll be looking at them one after the other. We have the esters, we have the ethers, we have groups like the alkanone. So these are examples of functional groups that gives each group of organic compounds or distinguishes it from another organic compounds. Just like I said, the homologous series, we've succeeded in explaining it under what a functional group is. So the homologous series are simply the group of organic compounds that we have. And this group of organic compounds, they are determined by the presence of the functional group. So when we have an homologous series, this is determined by the functional group. So the functional group gives birth to an homologous series. If we have a functional group, which is the hydroxyl group, we have the functional group, the hydroxyl group. It gives birth to a group of organic compounds, a family of organic compounds, which we know as the alkanones, or we can simply call them the alcohols. So this group of atoms is able to give birth to a group of organic compounds called the alkanol groups, or the alkanol series, or the alcohols. So I hope we understand what a functional group is and what an homologous series is, and we know how these relate to each other. Now, each group of organic compounds, they have what we call the general molecular formula for each homologous series. For each organic compounds, there are ways that we can determine the molecular formula for them using a general formula for the whole of the family. For example, we have homologous series like the alkane family, the alkane family. So this is the fundamental family or the fundamental homologous series in the organic compound. It has a general formula called that is represented as CnH2n plus 2. So this has a formula, and we have another homologous series, the alkene family, which is represented as CnH2n. We have another one called the alkyne family, which is represented as CnH2n minus 2. Now let's see how we can use this group of formulas to determine the families of organic chemistry that are found in the alkane family, the alkene family, and the alkyne family. So first of all, we're looking at the first and the fundamental family in organic chemistry, which is known as the alkane family. And let's use this formula that was given to generate their members. Each members are called homologous. So let's see how we can generate their members. The first organic compound or the first member in this family is what we know as the methane. A lot of you have heard of methane. When we started earlier, we say we have methane as one of the organic compounds that is found from minerals. It's also, they call it the natural gas in the petroleum industry. Now, this methane has a formula. We have this, we have this. So there are two atoms that must be found in all alkane family, which is the carbon and the hydrogen. So every alkane family must have these two compounds. Are we together? So it must have a carbon atom and an hydrogen atom. Now, N represented, or we can say N represent numbers. When we say N1, we mean the value. When we say N is 1, then the value of our C is going to be 1. So instead of N here, we are having 1 here. And our H is going to be what? Since we have 2 here, we put down our 2, and our N is what? Is 1. This is the first member, so it takes the number 1 position in this family. So we are going to multiply it by 1, and then we have plus 2. So the first member has 1 carbon. 2 times 1 is 2, plus 2 is equals to 4, and 4 hydrogen. So using this method, we can look for other members of this family. Let's look for the second member, which is going to be what? N is going to be what? N is going to be 2. So instead of 1 here, we represent it by what? By 2. We change our N here to 2. So here, carbon becomes 2. And 2 times 2 is what? Is 4. Plus what? Plus 2, which is going to be what? 6. And this second member is what we call the ethane. So using this formula, we can look for as many, or we can derive the formula, the structural formula or the molecular formula as much as we want. So let's say N equals to 15. So what we are going to have is what? C15, 2 times N, which is going to give us what? 30, right? Correct. So we have H here. 2 times 15 is going to give us 30, plus what? Plus 2. We are going to have C15, H32. And this is called the pentadecane. So I'm going to give you a tip on how you can remember the first 10 members on this alkane family. The first 4 member, I'm going to give you an acronym or a mnemonic. So I'm going to give you a mnemonic on how you can remember the first 10 members on the alkane family. Using this mnemonic, my elephant prefer banana for the first 4 members, and then from there we can use our polygon, which we know from mathematics. So my elephant prefer what? Banana. The M here stands for methane. The elephant, which starts with E, is going to be what? Ethane. The prefer, which is going to be P, is going to be what? Propane. And the B, which is banana, is going to be what? Butane. Now, these are the first 4 members on the alkane family. Now, like I told you earlier, right from the 5th member, we can use the basic knowledge of our polygon. When a polygon is 5-sided, we call it pentagon. When it's 6-sided, we call it what? Hexagon. When it's 7, we call it what? Heptagon. When it's 8, octagon, and so on. Now, using this format, let's say we have our pentagon. Now, what you are going to remove is you are going to remove this argon. Same way with the hexagon, you remove the argon. The heptagon, you remove the argon. And then all this, one thing you should know, all this family, the members of this family, they all end with the common name, N. So instead of argon here, our 5th member is going to be pentane instead of pentagon. The next member is going to be hexane, which is gotten from what? Hexagon. The next member is going to be what? Heptane, which is gotten from heptagon. We have octane from octagon. We have nonene. We have what? Decane, which is from what? Decagon. So using these tips, you can know the first 10 members that belong to this group of what? Organic compounds. So another group of organic compounds is known as the alkene family. The alkene family has a general formula of CnH2n. The first member is known as ethene. Now, take note of this. The value of N in ethene starts from 2. In our alkane, the first value of N was 1. But in this case, the value of N equals to 2. Now, looking at this, if we have a general formula of CnH2n, and we say the first member is having N to be 2. So what is going to be our formula, our molecular formula? So in this case, we are going to have C2H2 times what? 2, which is going to give us C2H4. So this is the first member on the alkene series or the alkene family. We have other members like the propene, the butene, the pentene. Now take note of this. Since you've known the first 10 members on the alkane family, it is very easy for you to know the first 10 members on the alkene family. What you are going to do is that this family has their name to end with in instead of in. So whatever name you have on the alkane family except the methane, you are going to end it with what? Ethene. Sorry, with in. So instead of ethane, we are having what? Ethene. Instead of propane, we are having propene. Instead of butane, we are having what? Butene, correct. So the next one we are looking at is the alkyne family. So after these 3 families, we'll move to our next subtopic. So another homologous series is what we know as the alkyne series. The alkyne series or the family of the alkynes. So they have a general formula to be CnH2n minus 2. So we can easily predict the first member on this family or of this family. So also take note, our n start from 2. So in alkane, n starts with 1, alkene, n starts with 2, and same with alkyne, n starts with 2. So if we have n to be 2, and this is our formula, then we are having C2, H what? 2 times 2 minus 2. So we are having C2, H what? 4 minus 2, which is going to be what? C2H2. So using our general molecular formula, we can dictate or name all the members of a family if we have the specific formula for that family. And now we'll be looking at another characteristics of homologous series, which we call the arithmetic progression. Now, in arithmetic progression, what's the basic thing you have to know there is that each member that belongs to a family, the next member, there is a specific difference that is within them. Take note of that. When we have member 1, member 2, member 3, there is always a specific difference that is within each member. Now, this is an example of what I'm trying to say. We have the first member on the alkane family to be the methane, which its formula is given as CH4. Now the next member is given as C2H 2 times 2, which is 4, plus 2, which is 6. Now the third member is going to be C3. Then 3 times 2 is going to be 6, plus 2 is going to be 8. Now there is a specific difference between them in the sense that if we minus this from this, there is a formula that is within them, or there is a formula difference within them. If we have C2H6 minus CH4, we are going to have CH2. 2 minus 1 is going to give us C, which is 1. And then 6 minus 4 is going to give us what? 2. Now, each member of this alkane family must be different from the successive one by this formula, by this molecular formula. So the next member should also have the difference of this CH2, or we can say molecular formula, molecular mass of 14. Are we together? So now let's try this within this member number 2 and member number 3. 3 minus 2 is going to give us 1, and 8 minus 6 is going to give us what? 2. If we continue, we are going to have this trend within this family. Now let's take, for example, the next member, C4. 2 times 4 is going to be 8, plus 2 is going to give us 10. So in this case, we are having 4 minus 3, which is going to give us C. 10 minus 8 is going to give us what? 2. Each member of a family, each successive member is different from the next member by a general formula of what? CH2. If you apply this to another organic compound, it's going to follow the same trend. For example, we have the first member on the alkene family to be ethene, which is given as C2H4. This is our formula, CnH2n. If n equals to 2, then H is going to be equals to 4. So if n is equals to 3, which is the second member, this is the first member. The second member, note we say our n starts from 2. So the second member, n is going to be what? To be 3. So in this case, we are having C what? C3. 2 times 3 is going to be what? 6. Our third member, in this case, carbon number is going to be what? 4. So we are having C4, H what? 8. Now let's try the same thing we did here. Now 3 minus 2 is going to give us C, which is 1, and 6 minus 4 is going to give us what? 2. Same here, we have 4 minus 3 is going to give us 1, and 8 minus 6 is going to give us what? It's going to give us 2. So when you have one member you can easily predict the next member by just this. So the next thing on our list is another characteristics of an homologous series, which is known as the similar chemical reactions. Each member of homologous series undergoes the same basic reaction with every other member. For example, the alkane family, they undergoes reactions like combustion. They undergoes reactions like the substitution reaction. So if the first member of the alkane family, methane, undergoes combustion reaction, then every member of this alkane family is going to undergo similar chemical reaction. Another group of organic compounds is the alkene. The alkene undergoes a kind of reaction that is known as the addition reaction. The alkane family doesn't undergo the addition reaction. So since the first member, methane, doesn't undergo addition reaction, we can easily say propane doesn't undergo addition reaction. We can say pentane doesn't undergo what? Addition reaction. But moving to the alkane family, which the first member, the ethene, undergoes addition reaction, we can say every member, the pentene, the hexene, the butene, they undergoes what? Addition reaction. So each homologous series undergoes what? Similar chemical reaction. And lastly, they have same functional group. They all have same functional group. For the alkane family, what we use in determining what we use in determining the functional group is the saturation of that compound. The number of bonds that compound has. For the alkane family, they are all saturated. They have a double bond between they have a single bond. Take note of that, not a double bond. They have a single bond between all the carbons. And then the alkene family, what we can use in saying that this is their functional group is that they all have double bonds. The alkyne family, they all have what? Triple bonds. So this is a way, or this in a way, we can say this is their functional group. So we can easily say, what is the functional group of the alkane family? You know, when I was listing the functional groups, I didn't list some of the hydrocarbons. We call these hydrocarbons. Take note of that. The alkane, the alkene, the alkynes. I didn't give you their functional group. So we can say their functional groups is the number of bonds they have. So the alkane family, we can say their functional group is going to be this. The alkane family is going to be this, and the alkyne family is going to be this. So these are what? Their own functional group. So next we are going to be talking about the characteristics of organic compounds. The first characteristics is the type of intramolecular bond. When we say intramolecular, we are talking about within a molecule. And we know that what makes up a molecule are atoms. So when we are talking about intramolecular, we are talking about what? The bond between each atom that make up a molecule. Let's represent this as a molecule. So the type of bond that connects each atom that forms a molecule is the covalent bond. So each carbon is always linked to other atoms by a covalent bonding. So within this molecule, the atoms that make up the molecule are connected to each other by a covalent bond. Now the next is the type of the intermolecular bond. Now when we are talking about we are talking about molecule and molecule. The first one is in within the molecule. Now we are looking about molecule and molecule. This is a molecule. Now if we have another molecule that have the covalent bond as the intramolecular bond, now what connects this bond to this bond is what we call the van der Waals forces. So within each molecule, the intramolecular bond that we have is the covalent bond, And in between molecule and molecule, we have a force of attraction known as the van der Waals force. This is a very weak force. Now, another characteristics of organic compounds is the solubility of organic compounds. Now, organic compounds, basically they dissolve in non-polar solvents. Now, we have solvents like water and several other solvents, but this is the most or the universal solvent that we know. And water is known to be polar. Now, organic compounds, they are usually non-polar, though some may be polar, and that is why we have some organic compounds that dissolves in water. But generally, the solubility of organic compounds is basically in other organic compounds, which are usually also what? Non-polar. So we have organic compounds to dissolve in solvents like benzene. This is an organic compound and it is non-polar. Are we together? Just like I said earlier, there are some organic compounds that dissolve in water. These organic compounds are somewhat polar. Examples of those kind of organic compounds are the alcohols. That is why we have diluted alcohols. If an alcohol does not dissolve in water, there is no way we can dissolve or dilute our alcohol. Now, since this alcohol can dissolve in water, it's somewhat different from some other organic compounds. We also have other groups like the carboxylic group. These are some organic compounds that can also dissolve in polar solvent. But take note of this, generally, organic compounds are known to dissolve in non-polar solvent. Non-polar solvent like what? Like benzene and so on. Now, we also look at their reactivity. Organic compounds are usually slow in reaction compared to compound like reactions like that we have within the acid and the base and so on. Those ones are rapid reaction. But when it comes to organic chemistry, it is usually a slow reaction. Now, these are some examples some characteristics of what? Organic compounds. Next, we are going to be looking at the division of organic compounds. I hope the way I explained that thing was understandable. So we'll be looking at the divisions of what? Organic compounds. Organic compounds is largely divided into two groups. We have organic compounds to be divided into how many groups? Two groups. We have the hydrocarbons and we have the substituted hydrocarbons. Now, just like the name implies, when we are talking about hydrocarbons, they are organic compounds that comprises of only hydrogen and carbons. That is the group of organic compounds that some compounds like the alkene, and the alkyne family belongs to. Because in their general formula, they only have two group of atoms, which is always what? The hydrogen and what? The carbon. Now, we also have another group of organic compound known as the substituted hydrocarbons. Now, in this case, we have other elements other than what? Hydrogen and carbon. Those group of organic compounds are things like the what? The alcohols. If you look at the functional group of the alcohol, it has this. Now, there is an introduction of what? Of oxygen. We can also call them the non-hydrocarbon. You can see it in that way. But it's better we call it what? The substituted hydrocarbon, because they also contain hydrogen and carbon, but in addition to this, they have other group of atoms. Now, the hydrocarbons are divided into the aliphatic hydrocarbons and the aromatic hydrocarbon. Now, the aliphatic hydrocarbons, they are the examples that I gave you earlier. They are compounds like the alkane, the alkene, and the alkynes. We always have them in this format, either this format or this format. In this case, we can say it's what is straight. It's straight chain. In this case, we can say it's branched chain. And take note, even in a cyclic format, we can even have them in a cyclic format. So we usually have them in a straight format, in a branched format, and in a cyclic format. But in the aromatic hydrocarbons, they are usually in a cyclic format. Now, we have the aliphatic hydrocarbons to be divided into other groups. We have the cyclic aliphatic hydrocarbon, and we have the acyclic aliphatic hydrocarbon. Just like I said, the aliphatic may be straight chained or branched chain. These are known as the cyclic. So we have this format, or we have this format to belong to what? Acyclic, or we can say non-cyclic. They are also aliphatic hydrocarbons, but they are what? They are non-cyclic. Examples are things like examples of the straight chain. We can have something like the propane, and examples of the branched chain. We can have something like what? Methyl propane. Now, under the acyclic, they are always in a circular format, and we always have a prefix for them, which we call the cyclo. They are just like the acyclic, but in this case, they are what? They are in a circular format. So we have things like the cyclopentane, we have things like the cyclobutane, we have things like the cyclohexane, and so on. But take note of this: all cyclic aliphatic hydrocarbon, the least one we can have there should have a carbon number 3. So the first member of the cyclic hydrocarbon is what we know as the cyclopropane. And this is easily understandable, because if we have the methane, there's no way we can cycle this because it has only one carbon. If we have the ethane, there's no way we can put this into a ring format. The only first member that we can put into a ring format is the propane, which we can have as this, as this, as this, and as this. And then we have the what? The aromatic hydrocarbon. The aromatic hydrocarbon, they are divided into 2 categories also. We have the benzoid aromatic hydrocarbon, and we have the non-benzoid aromatic hydrocarbon. Now, when we are talking about the benzoid aromatic hydrocarbons, they are aromatic hydrocarbons that are either the benzene ring or a collection of benzene rings. So examples, we have the benzene, which is the first member of the benzoid aromatic hydrocarbon. We have the next member, we have other members like the anthracene. We have other members like the naphthalene. So these are examples of what? Benzoid aromatic hydrocarbon. We have something like this. Or we should know, take note, these all are carbons. So we have this. This is the structural formula for a benzene. Now, all benzoid aromatic hydrocarbons should be a collection of this. So if we have another group, it should be something like this. Another group should be something like this. So they are all what? They are all unit of what? Benzene. And we also have the non-benzoid aromatic hydrocarbon. Examples are the furan, and we have others like the pyrrole. So these are examples of what? Non-benzoid aromatic hydrocarbon. Take note of this. We have this to be benzoid aromatic hydrocarbon, and we have what? Non-benzoid aromatic hydrocarbons. And examples of benzoid is things like benzene and anthracene, and examples of non-benzoid is things like furan, pyrrole. Now, next on our list is going to be the classes of carbon atoms. Okay, the next on our list is the classes of carbon atoms. Now, in all organic compounds, the position of the carbon atom in an organic compound can be used to classify carbon atoms into about 4 groups. Now, we have an example of an organic compound here. This is the first carbon atom, the second carbon atom, the third carbon atom. We have the fourth carbon atom, and by the time we move here, we have the second carbon atom, the first one, the first one, the first one, the first one. Now, carbon atoms are usually divided into groups like the primary carbon, or we say primary carbon atom. We have the secondary carbon atom. We have the tertiary carbon atom, and we have the quaternary carbon atoms. Now, when we are talking about primary carbon atom, take note of this. They are always the terminal carbons. Now, in these organic compounds, don't worry about the naming of the organic compounds. In this organic compound, this is an example of a primary carbon atom. One thing you should know about primary carbon atom is that they are always attached to one other carbon atom. We have this carbon atom to be attached to only one carbon atom, and hence is what? A primary carbon atom. We have this, another carbon atom, to be attached to only this, and hence is what? This is also a primary carbon atom. We have this to be attached to only 2, which is what? A primary what? Carbon atom. We have this to be attached to this, which makes it a primary carbon atom. We have this to be attached to only 1, which makes it what? A primary carbon atom. So what you should know is that when we are talking about primary carbon atom, how many other carbon atoms are they attached to? Primary carbon atoms are always attached to one other carbon atoms. Now, the secondary carbon atoms, they are usually attached to 2 other carbon atoms. Examples of secondary carbon atoms are all the number 2 carbon atoms on this organic compound. So we have this and this. Secondary carbon atoms are always attached to this, to 2. So we have this carbon to be attached to carbon number 4 and carbon number 1 only, which makes it what? A secondary carbon atom. We also have this to be attached to 1 and what? And 3, which makes it what? A secondary carbon atom. It's as simple as that. Then we have the tertiary carbon atom. The tertiary carbon atoms are carbon atoms that are attached to 3 other carbon atoms. For example, we have this. This is attached to carbon number 2, carbon number 4, and carbon number 1, which makes it what? A tertiary carbon atom. There is no any other tertiary carbon atoms that we have here, except carbon number what? Carbon number 3. Then we have the quaternary carbon atoms. They are carbon atoms that are attached to 4 carbon atoms. We only have one here, which is this. This is attached to carbon number 2. It is attached to carbon number 3. It is attached to carbon number 1, and it is attached to carbon number 1 again, which makes it what? A quaternary carbon atom. Take note, they are what? How many carbon atoms that a specific carbon atoms is what? Attached to. Not any other atom. Take note of that. If we have something like this, we have something like this, and we have hydrogen. Now, and we have this. We don't consider hydrogen. We only consider how many what? How many other carbon atoms that it is attached to, not any other element. So thank you very much. We come to the end of this tutorial. Watch out for our part 2. Thank you very much.